Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. I'd like to welcome all our members to the discussion for today, and kindly request us to subscribe, engage us in the comment section, and also ring that notification bell for updates on various discussions in math and sciences. Now, in our discussion today, I'm going to look at force on an electric charge moving in a magnetic field. And this, in a way, is going to complement on the previous video we had done on the relationship between a current carrying conductor and a magnetic field. So I'm going to use the same illustration for us to particularly create a relationship between these two specific concepts, whereby we are going to, in case of, instead of us looking at a current carrying conductor in a magnetic field, we are going to look at an electric charge. Now, from our previous discussion, we had defined or rather given a representation for a magnetic charge using this specific letter. Now, in this case, this can either be positively or negatively charged, which are among the two charges which exist in nature, as said. Now, we had said that basically when an electric charge is going to move in an electric field, this is going to be experiencing some kind of a force. Perhaps I can give that one a short summary statement. Now, in this case, we are going to see that when an electric charge is moving in a magnetic field, so I'm going to use the symbols. I presume that we understand what they imply. So when an electric charge is moving in a magnetic field, it is going to experience, so I can write it experiences a force given in terms of that specific symbol. Now, in this case, we are going to consider a number of charges which are going to pass through a specific point in a particular time frame, whereby we're going to have suppose n number. So this is going to be the number of particles, n or just n charges, which is a number of charges pass through a particular point in a time frame t. So take note of these specific symbols which are mapped, and we're going to create a relationship between them. So in this case, I've mentioned that if we have a charge moving in a magnetic field, it's going to experience a force. And then suppose we have a number of charges that are going to pass through a particular point in a magnetic field using the time t. We can have a relationship that is going to define the current which is going to flow in this specific case. Remember from our last discussion, we had defined current as the rate of flow of charge, and therefore gave it this specific ratio of a charge over time given as such. So we can define the total current which is going to be experienced by n number of particles as a product between the number of particles and the charge all over the time given as such, and that is going to be giving us the constituent current that is going to be experienced in this particular case using this specific equation. Now, suppose we consider the aspect of distance. So we have said that this is going to be the time taken, and then we have defined this is going to be the current and the magnetic field. So suppose we have this specific amount of charge that is going to travel through a distance given as L. We can incorporate distance as a factor in this specific case from a study of mechanics, whereby we're going to see that distance basically is defined as the product of velocity times time. Therefore, we can consider the velocity aspect of this specific particle that is going to move in this magnetic field. Therefore, we can give this specific aspect of the length covered by this particular charge in this time t as the product of velocity times time, and therefore give us a relationship of this specific nature, whereby we're going to have L as a product of L times time. Now, we can have this specific relationship combined to give a general equation, and this is going to be the equation from this specific discussion, whereby we are seeing a number of factors which are going to affect the force experienced by a current carrying conductor inside a magnetic field. Now, we had given that a specific relationship of a force experienced by this current carrying conductor in a magnetic field as a product of current flowing through that field, the length of this specific conductor, and then the magnetic field given in that specific case, and the angle of interaction which we had given in terms of theta given as such. Now from this specific relationship, we can infuse or include basically this specific aspect we have discussed of current and length, whereby I have said that basically we can have this current of n number of particles given using that specific ratio, and the length, as I have said, from this lower section is going to be the product of velocity and then time. So doing a substitution for these two specific factors, then therefore we are going to have this particular force given in terms of a charge, which is the product of nq all over t, and then we're going to have a velocity times time giving us length, and then we can have the b sine over theta given as such. And in this case, we can have a simplified version of this specific formula, and that is going to give us nq, and then we have a vb, the sine of theta given as such. So this is going to give us the force on one particle, or rather the force of n particles moving in this specific magnetic field. So we're going to look at force on an electric field, a charge moving in a magnetic field. So if we consider one of them, then therefore we can have this specific relationship given us for one particle, which is going to be given as such. We can have this one by, of course, eliminating this n number of particles, and then we are going to have the force given in terms of a qvb, the sine over theta, given as such. And this, of course, is the equation that is going to give us the magnitude of the force exerted by a magnetic field on a particle, of course, which is going to be moving at a velocity v in a magnetic field, which we have given in terms of this specific representation. Now, in this case, this, of course, generally is going to give us a basis for trying to, of course, show that one. And of course, from our previous discussion, I had mentioned that we can, using this specific relationship of the angle of interaction, we can define the maximum force experienced and the minimum force in that specific order. Now, in this case, I mentioned that the maximum force is going to be experienced when this particular angle of theta is equivalent to 90 degrees. And of course, we are going to have force minimum experienced when theta is equivalent to 0 degrees. Now, in this particular case, then therefore we can represent the maximum force experienced by these specific particles as a product of charge, velocity, and the magnetic field, whereby the force minimum due to this specific aspect, the sine of 0 basically is going to be 0, where the sine of 90 degrees is equivalent to 1, whereby this is a sine of 90 degrees 1, and then this is going to be 0, whereby the sine of 0 degrees is equivalent to 0. So in this case, this is going to be defining the maximum and the minimum force being experienced by these specific particles. Lastly, as well, we can define the distance or the direction of this particular particle, which is moving in, of course, a magnetic field, by giving it using the right hand rule, which we had, of course, mentioned in some of our videos. So in this case, we're going to have the force acting in that particular direction, whereby the current is acting in this particular direction, and then we're going to have these specific symbols indicating the motion of, or rather indicating, of course, the magnetic field moving into the board if we are to use this specific orientation from our side. So the magnetic field is going to go in that specific direction, the current and the force experienced going downwards. So kindly check our description boxes for various links of other similar videos. Subscribe and engage us in the comment section for other discussions in mathematics and sciences. So that is it for now, guys. By God bless you. Catch us in our next video.